Now we're going to talk about how you find a basis for both the null space and the column space of a matrix A. Let's start with the basis for the null space. So just as a reminder, the null space is all solutions x of the homogeneous equation AX equal to 0. And a basis is a linearly independent set of vectors that spans a subspace. To find a basis for the null space, the first thing we need to do is find the null space of A. So here I found the null space of A. So notice that A is already written in reduced row echelon form, and the pivots are identified here. So we find that x3 and x4 are free variables, and then we write the other quantities, that is x1, x2, and x5 in terms of those free quantities. This is something we've been doing for quite a while. Then we try to find the matrix X, and we're writing the solution in parametric form. So notice that the values x1, x2, and x5 have been replaced with the values that we have above. And if we write it in parametric form, we end up with x3 times this vector plus x4 times the second. So this set of vectors, 3, negative 2, 1, 0, 0, and negative 5, 1, 0, 1, 0, represent a spanning set for the null space. So the null space of A is a linear combination of these two vectors that we see here. And we can also write that as the span of those two vectors. So again, those two vectors form a spanning set for the null space. So it turns out the basis for the null space is simply those two vectors, because those two vectors, one, we already know they span the subspace, but they also are linearly independent, and that will always be the case when you're dealing with the null space. So the spanning set for the null space will also be the basis for the null space. So just to recap, if you want to find a basis for the null space, you do the following. You take the matrix A and you put it in reduced row echelon form. You identify the free variables. Then you write the other variables in terms of those free variables. Then you write the solution X in parametric form, and the set of vectors that you obtain, which is the spanning set for the null space, is also a basis for the null space. Notice that the number of vectors in the basis is going to be equal to the number of free variables in the matrix, or in the equation AX equal to 0. Finding a basis for the column space of A is extremely simple, and we'll see in just a moment why. So let's recall that the column space of A is just all possible linear combinations of the columns of A. So here I write the column space as a linear combination of all the columns in the matrix A. By definition, we can also write the column space as the span of the columns of the matrix A. So this tells us that the columns of A form a spanning set for the column space. In other words, we have a set of vectors that spans col A. So I have a set of vectors that spans the column space of A, but these vectors are not linearly independent. So to get a basis, I need a set that is linearly independent. Now, how do I know they're not linearly independent? Well, first of all, we have 1, 2, 3, 4, 5 vectors, and they are in R4, which tells us that we have an underdetermined system, which means that AX equal to 0 has free variables, which by definition tells us it is a linearly dependent set. So what do? Well, what we do is we use the spanning set theorem. And the theorem says the following. It says that if I have a set of vectors that spans a subspace H, okay, so this set of vectors spans H. If one vector, let's say the kth one, can be written as a linear combination of the remaining vectors, then if I take that vector out, so I'm taking out the one that can be written as a linear combination of the set, then the new set, which we're calling S, also spans H. So what does that say? It says that if I have a linearly dependent set of vectors, if I take out enough vectors until it becomes linearly independent, the linearly independent set still spans the subspace. So now I have this set H that simply contains all the columns of A, is a spanning set for the column space. Again, it is a linearly dependent set. So I just need to eliminate the ones that can be written as a linear combination of the other columns. Well, the way that I do this is I simply identify the non-pivot columns. That would be the column for variable x3 and the column for variable x4. I eliminate those, and what remains is a basis for the column space of A. So here is our basis, and notice that the number of vectors in the basis is given by the number of the non-pivot or the pivot columns of the matrix A. So let's recap the steps for finding a basis for the column space. The first thing we want to do is put the matrix A in row echelon form. It turns out that our matrix is already in row echelon form. The next step is to identify the pivot columns of A. So here we've done that. Here are our pivot columns. Step 3, go back to the original matrix. So ours is already, the original matrix we were given is in row echelon form. So those columns form the basis. But if we performed row operations on A to get to another matrix to identify the pivot columns, we would go back to the original matrix A and take those columns, and those columns would form a basis for the column space of A. So let's try a different example for the column space where the matrix A is not in row echelon form so that we can see the entire process at work. So first we take the matrix A and we put A into row echelon form, which is given here, and we identify the pivot columns of A. So notice that there are two pivot columns, which tells us that the basis for the column space is going to have two vectors. When we write the basis for the column space, however, we do not take the columns from the matrix B. Rather, we take the corresponding columns, so that would be the first column, and the third column from the matrix A to write the basis. So the basis of the column space comes from the columns of the matrix A, and that's given here. Now notice that just in the same way that the column space of A is equal to the span of all the columns of A, it is also equal to the span of the vectors that are within the basis. So it's the span of 1, 2, 3, and 3, 8, 11.